Probability and Statistics Hypothesis Testing Part 2. This is the follow-on from Part 1, which is in the same video series, and it is recommended that you also are familiar with the video on estimating population parameters, because that's also in this series, and references will be made to techniques in that video. So we've already established the steps in performing a hypothesis test. Set up the null hypothesis, the alternative hypothesis. Decide on the level of significance, whether you want 5%, 2.5%, 1%, relating to the 95, 97.5, 99% in the Z-score, etc. Establishing the acceptance region or non-rejection region and the critical or rejection region. Now that'll come into the estimating population parameters, because we need to set up areas where it is rejected. Selecting a sample, well, that's random, and collecting data from the sample. Selecting the sample is pretty complex, and you have to do it by rigorous means. Calculate the relative test statistic, in this case the Z-score. Use the calculated test statistic to determine if the sample statistic is close to the claim or not close to the claim. And from there, we accept the claim or reject the claim. So we either, if we accept the claim, we reject the null hypothesis, or we accept the null hypothesis. Let's look at an example. A sample of 64 items taken from a normal population, which means normally distributed, with mean 150 and variance 100. Now the sample mean is found to be 152, so now we're looking at the sample. Test at 5% significance levels the following hypothesis. Null hypothesis, that the mean is 150, and the alternative hypothesis that the mean is not 150. So there it is, normal distribution, 150, 100. That is the mean, that is the variance. It's two-tailed. The fact that it's not equal to means that it's at two ends. So now, if we're dealing with 5% significant level, that means we have to divide it between the two ends, getting 2.5, 2.5. So the Z-score for that will actually be 100 minus 2.5, so it'll actually be at 97.5. We need the Z-score. Notice 97.5, Z 97.5, 1.96. Now we use our formula. This is the formula to convert to the standard normal distribution, because obviously at this stage the sample doesn't necessarily have a normal distribution, a standard normal distribution. So we say the mean of the sample minus the mean of the population over the variance of the population divided by the square root of the number of items, which is 64. And we end up with 1.6. Now if you look at 1.6, 1.6 is going to put you sitting inside here somewhere, which means it's not out of the ordinary. It would have to be above 1.96, which means that that sample mean of 1.152 says acceptance region, we accept the null hypothesis. Insufficient evidence to reject the null hypothesis. Accept it. Right, sample of 36 items taken from normally distributed population with mean 83 and variance 100. The mean of the sample found to be 86.2. Test at the 5% significance level the following hypothesis. P equals 83. So this is now the probability. This is now for the sample. P greater than 83. H0 says it stays at 83, the mean of the sample, and this says it's greater than 83. And that is one-tailed. So in this case, where before we had 5%, so we did 2.5, 2.5, and made this 97.5 for your Z-score. This is now 5%, and because it's greater than, the whole 5% is sitting above here, which means we're now going to look for a Z-score at 95%. That's why I'm saying Z95 is 1.645. Right, same formula. We're going to substitute in mean of the sample minus mean of the population over the variance of the population. Well, actually the standard deviation, that's the variance, so we need to square root it to get the standard deviation over the square root of the number of items in the sample. That gives us 1.92. And that's inside here somewhere, which is greater than Z95, which means it's sufficient to reject H0, which means that in fact this says that this is actually a significant find, so something else must be causing it, except the alternative hypothesis. A company sells mathematics study guides, saying that students use their guides and improve their marks. Mathematics marks are known to be normally distributed with mean 70, variance 100, in other words, standard deviation 10. Random sample 36 students, and their mean mark is 73. So 73 versus 70. So we look at that normal out and we'd say, well, is that significant? I don't know. Well, it depends on the variance of the mean of the sample, you see. So the population. So let's test it at the 5% and the 3% significant level. It would be pretty obvious that because it's improved, we need greater than 70, mu greater than 70. And that means it's a one-tailed test. At the 5% level, we're going to find Z95%. There's 1.645. So, we're going to find the Z-score. Same formula. Which gives us 1.8. So this group getting 73% as a mean, when the mean here is 70% and variance 100, is actually significant. Now remember, rejection means rejecting the null hypothesis, because the null hypothesis is the not guilty. We're going to reject the not guilty. Reject H0, accept H1. So this says that the study guides are making a difference. Evidence is sufficient to support the company's claim that use of their study guides improves students' marks. Right, 3% level. It's still one-tailed. That's now 3%. So we're going to look at Z97. And the 1.8 is no good, so at the 3% level, it's not acceptable. And we accept H0, we reject H1, evidence is insufficient to support the company's claim. So in other words, it's all a question of choosing your confidence levels and deciding whether with probabilities. Comparing two different population means. Right. Comparing life expectancy of smokers versus non-smokers. So it's two different populations now. Math marks of boys versus girls in the same class. Science marks of two schools. This now involves two populations, two normal distributions, mu x, variance x, and mu y, variance y. The null hypothesis says there's no difference. The alternative hypothesis says there is a difference, they're not equal, or the one's bigger than the other, or the one's smaller than the other. So there is your normal distribution now. Notice that we add the variances. So the formula is converted to this. Pretty straightforward. New mean, there's the old mean, and there's the variance. Square root of it. You see, this is really the square root of the variance over n. Give you the standard deviation over n. Here now we've got the square root of, and we've got the variance over n because we can't square root because of the plus sign between. But because the null hypothesis says ux equals uy, we can actually remove that, because that's naught. And there's our formula. So, let's have a look at this, comparing. Random samples from two normally distributed populations have the following results. Nx, the mean, the variance, ny, the mean, the variance. Perform a test to decide if there is a significant difference between the means of the two normal distributions at 5% significance. It's two-tailed because it says just is there a significant difference. Therefore, 5% level, we need to divide the 5% to 2.5 on each side, which means Z score at 97.5. We're going to apply our formula. Remember, our x minus y went, our averages went because they're supposed to have the same. There's no difference, it says. There we substitute in to get negative 1,67. Well, it needs to be either below negative 1,96 or above 1,96. So in fact, there's 1,67 there, and there are the tails there. So we're going to accept the null hypothesis and reject the alternative and say no significant difference between the means. Another example, in an examination which was taken by a large number of students, the marks were normally distributed with a standard deviation 20. Two schools each entered 100 candidates, and the mean marks for the two schools were 58.5, 53.5. Is there a significant difference between the results of these two schools at the 2% significant level? Now, all it's talking about is a significant difference, which means that it's two-tailed, so we're going to have to divide that 2% into the two ends. So we're going to be looking at 99% for the Z-score. There are the two distributions. There's H0, the null hypothesis says no difference between them. and H1 says that they're not equal to one another. So we divided 1%, 1%, which means I'm going to look at Z99 there. And either I need bigger than 2.330 or less than negative 2.330. So our formula. 1.767. Oh, that's well within the acceptance region. So therefore we accept the null hypothesis. We accept it because it's well within the region. It's quite acceptable. It's quite normal. No significant difference between the school's results at the 2% level. Creamy Dairy claims they produce the richest milk in the region. They claim their milk contains more than 5% more butterfat than their closest competitor, Rich Dairy. A random sample of 61-litre containers of the Creamy Dairy milk showed the mean butterfat content was 3.55% with a standard deviation of 0.3. Rich Dairy asked Creamy Dairy to defend their claim. An independent assessor is selected to test the butterfat content of milk samples from each. The mean butterfat of 61-litre sample from Rich was 2.95 at standard deviation 0.2. Test at 1% level the claim made by Creamy Dairy. There's not a claim that they're not the same. And it's not a claim one's greater than the other. It's a claim that one's greater than the other by more than 5%. So we're coming back to this formula here with the extra bits on the end because they're not equal to one another. Which means, in fact, though, that if you look, we can still substitute there, but we're not going to put naught. We're going to have an extra amount on the end. So there we have those measurements. It's one-tailed because it's greater than. We're going to look at 99% because it's one-tailed at 1%. And we're going to have 0.5 slotted on the end there because of that difference they claim. .33 is the z-score for that one. It's less than 2.33. So we accept the null hypothesis because it is in the acceptance region. It's lower than the actual extreme z-score. So Creamy Dairy, bad luck.